Hey, welcome back to chemistry. So we've been looking at gases and looking at some reactions that are in the atmosphere, and it's a convenient time to take a look more generally at some of the things that are happening in the atmosphere and using chemistry to understand why that's what's happening and what we do about it. So there are some interesting things. Let me point out a few of them, and now that you have a bit of chemistry under your belt, you should be able to understand these at a more detailed level and understand also the solutions to these things. So one of the things that I think is an interesting question is that if you look across the universe, by far the most abundant element is hydrogen, and the next most abundant one is helium. So across the universe, 99% of all elements in the universe are hydrogen. However, if you look in our atmosphere, we don't have a lot of hydrogen gas floating around by itself. And why is that? So we don't find a lot of helium floating around by itself either. Why is that? Well, you may recall that we have this idea of, we call the kinetic molecular theory of gases, which is a long way of saying that temperature and motion are the same thing. So the faster something is moving, it's a higher temperature. Right? So when you heat up a gas, what you're really doing is you're increasing the motion of that gas. So something that's a higher temperature has a higher kinetic energy and a higher velocity. We also had this idea that, well, all molecules are not moving exactly the same speed. So if I look, and this is at room temperature, so if I look at gases at room temperature, I'll find that something like hydrogen, this orange line, on average is moving between 150 and 200 meters per second. But that's the average, right? And you can see from this broad distribution that some are going really slow and some are going very fast. And this tail sort of goes on for a long ways, right? So there are some atoms that are going to be, or some molecules of hydrogen that are going to be going even faster than the maximum on this graph, which is 3,500 meters per second. It's worthwhile noting that if you want to get a spaceship off the surface of the Earth, right, if you get it going at 11,200 meters per second on the surface of the Earth, then it will escape the gravitational pull of the Earth. Right? So we call this escape velocity. So anything that's going at 11,200 meters per second here on the surface of the Earth has enough kinetic energy and enough velocity to be able to escape from the gravitational pull of the Earth. So it doesn't matter about the mass of the thing, it only matters how fast it's going. Now you may notice this distribution, the speed distribution, that hydrogen gas, maybe a fifth as fast as the escape velocity on average. And so that means that some atoms are moving much faster than that, and some are going fast enough to escape from the Earth. And this is one of the things that contributes to the hydrogen being less here on Earth, is that the hydrogen is moving so fast at room temperature that it's going fast enough, a few of them are going fast enough that they escape. They escape the gravitational pull of the Earth and they're gone into outer space. There are other things that are going on as well, but this is one of the reasons that we have less hydrogen and also a little bit less helium than you'd predict. So these lighter gases are going super fast, and it makes it easier for them to escape from the gravitational pull of the Earth. Let's think about Mars, right? So Mars has very little atmosphere. It is also a smaller planet and has less gravity. So you'll weigh, I don't know, maybe half as much when you're on Mars as you are on Earth. So the gravitational pull is less. And remember that the daily temperature, some places around the equator of Mars, they can get up to nearly room temperature here on Earth. So the temperature can get quite high, relatively high on Mars. And that means that you'll have molecules that are moving very fast, and the escape velocity is much less, right? So on Earth it was 11,000 meters per second, and on Mars, anything that's going 5,000, less than half as fast, 5,000 meters per second, has enough kinetic energy to escape from the surface of the planet. And you look at something like hydrogen, and even more hydrogens, there's a better chance that some hydrogen molecules are going that fast and they just escape. So no matter how hard you try, you will not be able to keep hydrogen on the surface of Mars. It's going to fly off So some will be going slower and some will be going faster, and those ones that go too fast are gone, and you can't get them back. So, in Mars we'll find has a thinner atmosphere, but also probably always had a thinner atmosphere just because it has a harder time hanging on to things, because gases are moving, and some gases are moving really quickly. The smaller ones on average are moving very quickly, and even within the smaller gases there's a subset that's going to be going super fast. Continue our tour through the solar system. So did you know that Venus is not the closest to the sun, right? Mercury is the closest to the sun, but it is the hottest planet. So we estimate that on the surface of Venus, the temperature is between 800 to 900 Fahrenheit. So that's hot enough to melt iron on the surface. Why is this, right? So there are two images here. So one is what we see through telescopes. If you can magnify it enough, you see the surface, you see the cloud covers on Mars. And then the other one is sort of a heat diagram of Venus, and showing this sort of river of hotness that runs through the atmosphere. So it's a very chaotic and violently moving surface that's really hot too, right? So no probes that we send there can survive, right? They just melt, and they just die when they get close to the surface. But why is this, right? So, well, we can understand this, right? So it's due to the atmosphere of Venus, and it turns out that Venus's atmosphere is about 97% carbon dioxide and only 3.5% nitrogen, right? And that carbon dioxide is really good at trapping heat. So think about this. So Venus has this atmosphere, this thick atmosphere, which contains a lot of carbon dioxide, and that's really good at trapping heat. We call this the greenhouse effect. And what do we mean by that? Well, light can pass through the atmospheres, fortunately, so we can see things, and that light brings energy in. Remember, light is a form of energy. When it strikes something, that heats it up. So you feel this effect when you go outside in the sun, that it heats up, and what that is, remember, heating is just more motion, right? So it's converting that light energy into motion energy or temperature. So things are heating up. And when you have an atmosphere, especially one that contains carbon dioxide, that the heat doesn't readily escape, and so it accumulates. And so you end up having something that accumulates heat over time, versus something closer to the sun like Mercury, which doesn't have this atmosphere and it doesn't retain that heat. That jiggling motion gets transmitted back out into the outer space. So the heat just doesn't escape as much. And importantly, it's important that the increased carbon dioxide acts as this heat trap, so it helps retain the heat. You may know where this is going, right? So if we think of the atmosphere on Earth, right, it's a much different constituents, right? So here on Earth, we're 78% nitrogen, 21% oxygen, and a little bit of argon. All the other gases are pretty small amounts, including these listed here. They amount for 1/10 of 1%, but they're important. And it's curious also to think about water vapor. So water vapor varies quite a bit, right? So when you look up and you see clouds, right, there's more water vapor than on a clear day, right? So this varies across the place. And in some places that are cold, they have less capacity to hold water vapor, and so we find a smaller percentage of water vapor. And in places that are humid, we find a higher percentage of water vapors. But many of these gases can behave as carbon dioxide does to trap heat. And carbon dioxide has this behavior where it's effective at trapping heat. Water vapor also has this behavior. So water vapor is good at trapping heat. We call it a greenhouse gas. CH4, methane, is also good at trapping heat, and it's a greenhouse gas. And all of these gases and others have this property. The challenge is that the amount of CO2 is increasing, and that's causing global average temperatures to increase, and this is having serious effects. A couple of things that are interesting to look in the atmosphere. So smog, so you should be able to understand a little bit more about how this works. So let's see. So smog is a combination of smoke and fog originally, and there are really two main types of this. So we have sulfurous, so London smog, and photochemical, also known as Los Angeles smog. Right? And they got quite bad. So there are outbreaks, or there are periods of time where in London and in Los Angeles where there were many deaths that were attributed to the longevity of the fog and of the smog that was there. So London smog generally comes from burning sulfur-containing materials, right? So if we burn coal that's high in sulfur, or diesel that's high in sulfur, we get these chemical reactions. I've shown you these before, but let me remind you about it. So sulfur in its solid form is going to be an octet, so it's going to be S8. I'm going to combine that with O2, right? So I'm burning this, and that's going to generate these SO2 molecules. The SO2, now a gas in the air, can combine with oxygen, and I can get the SO3, and this is something that happens in the atmosphere. And so far, it's not so bad. But the bad thing happens when we combine it with water, and this is going to lead to sulfuric acid. Right? So I'm going to take my SO3, I'm going to combine it with H2O, and I'll get sulfuric acid, H2SO4, and this is nasty stuff. This is bad stuff. So what's shown on the right here is an acid-damaged swamp, and what's on the bottom is actually lung tissue. So acid in the lungs are really bad. So it really depends where the water is acquired, right? So sulfuric acid, if it comes from rain, so if this water in this molecule or in this reaction comes from rain, then I'm making acid rain, and that's falling into the atmosphere, and that's bad for whatever it falls on. But also notice your lung is a moist environment. So breathing in SO3, and that water that's inside your lungs can react with SO3 and can produce this sulfuric acid. And this is a thing that causes lung damage and can lead to deaths. It's quite a serious thing. So where the acid forms makes a big difference. If it's coming from the water in your lungs, this can lead to lung damage. And this was the basis. I mean, this was, at some point, this was intentional. So you may recall World War I, where they used gases to try to defeat the enemies. And several of these gases were based off of this principle that you have something that reacts with water, and if it reacts with water inside a person's lung, then it will cause damage and can kill them. So a horrific way to die. But the chemistry is very similar to the acid rain that's happening, and we can experience that around us. Second type of smog is called photochemical smog. So it comes from a couple of different routes. So one of these is a little bit more complex than I want to go into, from incomplete combustion of hydrocarbons and carbon monoxide. But this is one path that you can get these, and it's relatively straightforward to explain. So one of the byproducts of combustion is that we'll burn stuff, but there's a lot of nitrogen there, right? So our atmosphere contains a lot of nitrogen. So this nitrogen can combine with oxygen, essentially burn, and I generate these NO2 molecules, so nitrogen dioxide. This can be reduced, or I can essentially eliminate these NO2s by use of catalytic converter. And this is a historical problem that has really been addressed, but we're not at the problem yet. So sunlight is a challenge. So once in the atmosphere, these nitroxides, both nitrogen monoxide and nitrogen dioxide, we'll focus on the dioxide, they can absorb energy from the sun, and they combine with oxygen again, right? So I have NO2, I'm going to combine that with oxygen, and I'm going to get out a nitrogen monoxide and an O3, and this is ozone. And ozone is a great thing when it's in the upper atmosphere. So ozone in the upper atmosphere blocks some of the high energy radiation coming from the sun and prevents damage to us down here on Earth. But down at the ground level, ozone is relatively toxic. So ozone is highly reactive, and something that if you breathe it in too much, it can also damage your lungs. It's worthwhile noting that the nitrogen container, the nitroxides, are the thing that give smog its brown color. So if you see the brown color, that's nitrogen monoxide, nitrogen dioxide, sometimes nitrogen trioxide. So these are nitrogen-containing compounds. that are floating around. And if there's a lot of those floating around on a sunny day, you're going to get ozone, and that's going to be bad. It's going to be unhealthy for people. So I like these examples because there are some examples of things that have been historically a problem, but they've been fixed, right? So if you go to Los Angeles today, it's a much healthier place to breathe air than it was 30 or 40 years ago. And this is chemistry, right? So chemistry is a way of helping you understand the world around you and understand it at a detailed level. And the understanding can lead to things that you can fix. So ozone depletion. So we have had a problem of ozone depletion, and we've enacted globally laws to prevent the use of certain refrigerants which lead to the ozone depletion. And this has had a big effect. Acid rain used to be much worse. It's still an issue in many places, but it used to be much worse. And we switched now to, we don't use high sulfur coal, and we use very little high sulfur diesel. So just being careful what we burn makes a big difference. And photochemical smog, as I mentioned, the catalytic converters are really effective at reducing the nitroxides that get released from combustion or internal combustion engines. So these things have been had really successfully been addressed by understanding the chemistry of what's happening and coming up with solutions to that. Sometimes it's avoiding it. There is, of course, one thing which has not been effectively addressed, and that is the increasing global temperatures. And again, I think understanding what's happening and how that's happening and the chemistry of that is helpful for figuring out what to do about it. Anyway, I hope I hope you're able to use your knowledge of chemistry and your skills in chemistry to be able to understand the world around you a little bit more. And certainly these examples are intended to give you some insight into some of the things that are around us, and there are many more things that are good to understand. I hope that helps. Talk to you soon. Bye.